In this video, we'll take a brief look at the basics of calibrating polarization data.
There are a number of astrophysical phenomena which can generate polarized emission at the wavelengths observed by ALMA. Depending on the scientific questions you are interested in, well-calibrated polarimetric observations may be of critical importance.
First, let's look at what we mean by polarization. Electromagnetic radiation can be viewed as a transverse wave, where the electric field oscillates in a direction perpendicular to the direction of motion. Here we see an electromagnetic wave traveling in the z direction, with the electric and magnetic vectors oscillating perpendicular to each other in the y and x directions respectively. For clarity, we'll only show the electric vectors from now on. When the electric field oscillates in a single plane, as we see here, the electromagnetic wave is said to be linearly polarized. If the electric field direction rotates as it propagates along the z direction, the wave is said to be circularly polarized.
For most astronomical sources, the combined electric vectors of the radiation field from the source are oriented completely randomly, where each individual electromagnetic wave from the source has an electric field with a different orientation. Such sources are called unpolarized. However, in some astrophysically interesting sources, the electric vectors are preferentially oriented in one direction. These sources are called polarized.
At submillimeter wavelengths, magnetic fields are an important means of generating polarized emission. For example, dust grains tend to spin around an axis along the direction of the local magnetic field, leading to emission which is linearly polarized and oriented perpendicular to the magnetic field. In addition, electrons spiraling in a magnetic field yield polarized emission, which can be both linearly and circularly polarized. Molecular spectral lines can also be polarized when emitted in the presence of magnetic fields.
Another means of generating polarized emission is from scattering, particularly in dense regions like circumstellar disks.
Before we delve into how ALMA measures polarization, let's briefly review Stokes parameters.
These four parameters, usually called I, Q, U, and V, can be used to completely describe the polarization state of an astronomical source. I describes the total intensity of the source, Q and U describe linear polarization, and V describes circular polarization. Each of these can be derived from the output from the ALMA correlators.
But what is that output? As we learned in another video, each ALMA receiver is able to measure separately the electric field strength in two orthogonal directions, labeled X and Y. After mixing with a series of local oscillator signals to create sidebands, basebands, and spectral windows, the X and Y signals from each receiver are fed separately into the correlator. Inside the correlator, the X and Y signals from each pair of antennas are combined in four different ways: XX, YY, XY, and YX to generate visibilities.
But before the correlator products can be used to generate the Stokes parameters, they must be calibrated for various instrumental and atmospheric effects. If we're not interested in polarization and only want the total intensity of our science target as a function of wavelength, then we only need the Stokes I, which is a simple sum of the XX and YY correlator products. These data only need to be calibrated for the flux density, bandpass, and phase variations, as we've discussed in our Introduction to Calibration video. For full polarization observations, however, and to derive the Stokes parameters Q, U, and V, we need the XY and YX cross correlations, plus the difference between the XX and YY correlations. This extra layer of complexity requires extra calibration steps due to instrumental and other effects. Let's take a brief look at the most important of these effects that require calibration.
The first and most important of these effects arises because of something called leakage or crosstalk between the polarization signals, caused by the receiver cartridge design and external optics, and is different for every receiver and antenna. The splitting of incoming radiation into two orthogonal components in the ALMA receivers is not perfect, and some of the X polarization signal can leak into the Y channel of the receiver, and vice versa. This contamination produces an instrumental polarization. Even a completely unpolarized source, if uncalibrated for leakage effects, would appear to be polarized due to the instrumental polarization. This is most clearly seen in these images of Stokes V, which is sensitive to circular polarization. For a source without circular polarization, Stokes V should be uniformly zero, as shown on the right. But the instrumental leakage measurement, shown on the left, clearly shows non-zero Stokes V signal. For a linearly polarized calibrator like 3C286, the presence of an instrumental polarization signal is evident, as these images of Q and U before and after leakage correction illustrate.
As described in our previous video on an introduction to calibration, phase errors can be introduced into radio observations from atmospheric and other effects. Polarization observations have an additional complexity due to phase shifts or delays between the X and Y polarizations. These arise due to variations in the X and Y signal paths in each receiver, introducing a delay that must be corrected. In addition, the practice of arbitrarily setting the phase of one antenna to 0 also introduces another phase shift in offline cross correlations.
In order to calibrate or correct for these effects, we need to observe a polarization calibrator. Fortunately, the quasars that ALMA uses for bandpass calibration also make excellent polarization calibrators because they are bright, compact, and are scattered across the sky. These calibrator sources are also observed frequently by ALMA, every few days, in order to monitor their flux densities and polarization properties, and to check for source variability. Those which are both bright, relatively stable, and have polarizations of more than a few % can be used as polarization calibrators, and are selected at the time of observation by ALMA.
Each observation of a polarization calibrator detects the combination of the instrumental polarization, which is at a fixed angle with respect to the ALMA receiver, and the inherent polarization of the calibrator itself, which is oriented at a fixed position angle in right ascension and declination. As the sky rotates, the orientation of the calibration source's polarization vector changes with respect to the ALMA receivers, while the instrumental polarization does not. In order to disentangle the instrumental and calibrator polarization and to measure the phase delays and other effects for each antenna, the period of observation must be long enough to ensure that sufficient sky rotation has occurred. In practice, this is typically 2 to 3 hours.
Armed with this, we can now derive the polarization calibration tables, which are then applied to the full set of XY and YX visibilities from the science targets. With fully calibrated XX, YY, XY, and YX visibilities, we are ready to generate all 4 Stokes parameters to calculate the polarized flux, position angle, and other properties, and to generate polarimetric images. It's time to do some science.
We've just taken a brief look at how ALMA polarimetric data are calibrated. If you want to know more, the ALMA Technical Handbook has a more complete description of this process, plus details about additional effects and when those need to be addressed. Please check out our other videos, some of which are shown on screen now. Happy observing!